Welcome to this explainer, brought to you by Forge College. I was just looking through today's source material, and honestly, I am so excited to unpack this with you. Today, we're taking those pristine, theoretical energy spreadsheets you might be used to, and we're just throwing them right into the messy, constrained, but absolutely fascinating real world of renewable energy integration and Bitcoin mining. Here's our quick roadmap for today. We're going to cover 1. The foundation, 2. The variables, 3. The bottlenecks, 4. The synthesis, and we'll wrap up with 5. The final test. Let's just jump right in. Section 1. The foundation. Baseline modeling. Okay, so before we introduce the chaos of the physical world, the absolute bedrock of all this modeling comes down to one single number, 8760. Why? Well, because that is exactly how many hours are in a year. That constant is literally the anchor we use for calculating both annualized electricity consumption and peak demand. It all starts right there.
Section 2. The variables. Real-world constraints.
Now this is where things get really interesting, because we have to introduce a massive real-world twist. You see, the sun actually goes down, right? The wind randomly stops blowing. Your perfect spreadsheet suddenly needs a serious reality check. To model this, the material introduces something called the capacity factor. Simply put, it's just the ratio of actual electrical energy generated compared to the maximum possible output over that same time. Because as it turns out, a massive 100-megawatt solar farm is notoriously bad at its job during the night shift.
Looking at the actual data really puts this into perspective. Utility solar sits at around a 10 to 25% capacity factor, mostly due to clouds and, well, the Earth rotating. Onshore wind is a bit better, at 20 to 45%. But check out geothermal down at the bottom. It provides this incredibly stable, near baseload capacity factor of 70 to 95%. It's an absolute powerhouse.
But here's the catch, and it's a big one. Having a high annual capacity factor doesn't actually save you from a diurnal mismatch. That's a very fancy, technical way of saying your energy generation timing just doesn't line up with your demand timing. And since Bitcoin mining rigs run hot 24/7, you're going to need to figure out grid backup or storage for when your renewables decide to take a nap.
Section 3. The bottlenecks. Geographic realities.
So let's say you found it. A ridiculously windy, sun-drenched plateau that looks absolutely perfect on a map. Even if the weather cooperates flawlessly, you still have to deal with the physical limits of the Earth. We have to ask the multi-million-dollar question, can we actually deliver this power? Can you physically get those green electrons from that remote plateau to your actual mining rigs? The source material highlights these massive real-world bottlenecks. First, grid capacity. Can the local grid even handle your load without melting down? Second, transmission. Are there lines running to your site, or do you have to build them? Third, land usage. Is the terrain actually usable to build out your infrastructure? And finally, permitting. Because let's be real, a 24-month delay just to get local zoning approval will completely derail what looked like a theoretical dream site.
Section 4. The synthesis. Scenario comparison.
Okay. As we always say, raw data is pretty much useless until you synthesize it into a tool you can actually use. To build a refined scenario for comparison, the process boils down to 3 main steps. Step 1, identify your renewable nameplate capacity. Step 2, multiply that by our favorite number, 8760, and your capacity factor to get your estimated annual generation. And Step 3, aggressively apply all those geographic constraints we just talked about as your ultimate reality check.
When you actually run the math, the results can be pretty surprising. You might find that your so-called 100% green site still heavily relies on the grid. In this specific example from the material, solar meets 18% of the load, wind meets 30%, which means a whopping 52% still requires grid or backup power just to keep the machines running through all that intermittency.
So how do we compare different locations? By combining all these variables, we can rank scenarios using a site suitability score. This simple equation is basically magic. It turns those frustrating qualitative bottlenecks into a hard quantitative judgment about where to actually spend your capital and build.
Section 5. The final test. Feasibility versus delivery. We've arrived at arguably the most important mental model of this entire explainer. This is the concept that determines if a mining operation succeeds or if it just stays a fantasy on a laptop screen. You have to strictly separate annual energy feasibility from operational deliverability. Feasibility just asks, can renewables meet the total annual consumption? That's a math equation based on averages. But deliverability asks, can those electrons be delivered exactly when and where the miners need them? That factors in physics, grid capacity, and the messy reality of land rights.
Which brings us to the golden takeaway of everything we've talked about today. You can't mine Bitcoin on theoretical energy. Theoretical energy is absolutely fantastic for spreadsheets, it really is. But only deliverable energy actually produces hashes.
So hold on to that site suitability formula, because in our next explainer, we'll be diving into strategies for improving mining efficiency, exploring how load shaping interacts with this renewable supply. But I want to leave you with a question to ponder. As renewable integration gets more and more complex, will the most successful miners be the best engineers or the best geographers? This explainer was brought to you by Forge College. Be sure to visit forge.college to dive deeper into the subject and explore our comprehensive Web3 tracks. Thanks so much for hanging out, and I'll see you in the next one.